Hello friends, and welcome to another lecture on chemical engineering thermodynamics. Today we will learn how to calculate the change in internal energy, the change in enthalpy, the heat and work for a reversible constant pressure process. The fluid is an ideal gas. Let's first visualize what is a constant pressure process. If we take the pressure on the y-axis and volume on the x-axis, then the process from state 1 to state 2 is a constant pressure process. As is evident, the pressure is constant during this entire process. Now, the temperature is T1 at point 1 and T2 at point 2. So, let's make a note of it. The temperature at point 1 is T1 and the temperature at point 2 is T2. Now, as we can see here that the volume changes. The volume has increased. Pressure is constant, the volume has increased. So therefore, it's an expansion process. We can do the reverse of this also. We can compress the gas. Then it will go from 2 to 1. The process will go from point number 2 to point number 1. Now we apply the first law to this process. We assume that the system is a closed system. So the number of moles N is constant. Applying the first law, we get du is equal to dq minus p into dv. We add dpv on both the sides. Therefore, we get du plus dpv is equal to dq plus v dp. Since dpv is equal to v dp plus p dv. We all know that H is equal to U plus PV. Therefore, we get dH is equal to dQ plus V dP. Since the process is a constant pressure process, this term is 0 and we get dH is equal to dQ. So, for a constant pressure process, the heat given is equal to the enthalpy, and this is written as Cp, which is the heat capacity of an ideal gas at constant pressure, into dT. Integrating, we get delta H is equal to Q is equal to, we must N here, N Cp T2 minus T1, or this can also be written as N Cp delta T. Therefore, we have now the equation for the heat and the change in enthalpy. Now, the change in internal energy is equal to the change in enthalpy minus delta V into P minus P into delta V into delta P, since H is equal to U plus PV. Therefore, we get delta U as the second term obviously is a 0, we get delta H minus delta V into P. Written in a differential form, this is du is equal to dH minus P into dV. Now, for an ideal gas, PV is equal to nRT, which on differentiating yields dPV plus PdV is equal to nR dt. Now, when we replace this equation in this equation, we get du is equal to dH minus nR dt. It should be noted here that this term is 0 since the pressure is constant. Therefore, we get du is equal to n into Cp into dt minus n into R into dt. Collecting the like terms, we get du is equal to n into Cp minus R into dt. Therefore, du is equal to n into Cv into dt, since Cp minus Cv is equal to R for a constant for an ideal gas. Therefore, the change in internal energy for an ideal gas undergoing a constant pressure process is nothing but N into Cv into delta T, or N into Cv into T2 minus T1. Now, the work done can simply be calculated by change in internal energy is equal to the heat given for the process, which in this case is NCP into delta T minus or plus the work done. So, the work done is equal to N into Cv into delta T minus N into Cp into delta T, or work done is going to be equal to, collecting the like terms, we have Cv minus Cp into delta T. Now, this we know is minus N into R into delta T, or the work done by applying the ideal gas law can be written as minus N into R into T2 minus T1, which is going to be minus N into P, that is the constant pressure, into V2 minus V1, or the work done is equal to minus N into R into V2 minus V1. So, this is the expression for the work done. So, to recapitulate, a small correction. Yeah. So, to recapitulate, we have heat as equal to delta H, which is equal to N into Cp into delta T, and the delta U for the process is nothing but N into Cv into delta T, for a constant pressure reversible process of an ideal gas. So, this is all, guys. Bye and keep watching.